Okay, this is a review of the content from Chapter 3, which deals with electromagnetic radiation. Now, in this chapter, we're going to be primarily looking at radiation, electromagnetic radiation, as a wave type of a phenomena. In Chapter 4, we're going to consider how electromagnetic radiation can also behave like particles. But for now, we're going to just focus on the wave aspects and the wave characteristics of electromagnetic radiation. So here we have a sort of a definition that we can think about what electromagnetic radiation represents, and it is a transmission of energy through space without a physical connection through varying electric and magnetic fields. And the most familiar example of electromagnetic radiation is light. Now, when we say light, usually we sort of think about visible light, the portion of the electromagnetic spectrum that we can see, the colors of the rainbow, Roy G. Biv. And those are, of course, red, orange, yellow, green, blue, indigo, and violet. All the colors of the visible spectrum. And that's what we normally think about as light. Now, as we'll see, we can also mean more than that, because as you guys probably learned in grade school, out beyond the violet portion of the spectrum that we can see, there's electromagnetic radiation that we can't see. And out here we have ultraviolet radiation, and then we would have X-rays, and we would have gamma rays. On the other side, we have infrared and then radio waves. And so the electromagnetic spectrum extends far out beyond what we as human beings can perceive. And I like to describe this because most people are familiar with dog whistles. They know that there are frequencies of sound that dogs can hear that humans cannot. And so there are actually whistles that you can buy that you can blow. And if you're any distance away from that whistle, you can't hear it at all. But a dog, 300 yards away will be like, "Whoa, what's that?" And that is sort of the same sort of phenomenon. There are frequencies of light or frequencies of electromagnetic radiation that we can't see. And so we're going to talk about how those all relate to astronomy as we go. Now, when we say a wave, generally what we mean is this. A wave is really just a traveling disturbance. Now, for most waves, there's some sort of medium. If you have a wave passing through water, then water is the medium through which the wave passes. Sound waves usually travel through air, although they can also travel through liquids and solids as well, as we'll see later on. But light, actually, electromagnetic radiation, is special in that it can travel without a medium. But regardless of what kind of wave you have, a wave is simply a traveling disturbance, generally one that transmits energy. Now, we can talk about wave motion up here. It says wave motion transmits energy without the physical transport of material. That may be a little bit confusing, so let's talk about what that means, because that's something that's very characteristic of waves, particularly when we're talking about waves moving through a medium. I like to do a demonstration when I teach an in-person class where I'll ask for some volunteers from the class, and 4 or 5 students will come up. And I'll ask them to stand in single file. So I'll have a student here, a student there, a student there, and they'll all be facing the wall over here somewhere. And then what I'll do is I'll come behind this student and I'll push his back, and he'll move forward and he'll hit the student in front of him. And maybe it's a girl, so she'll go forward and he'll come back a little bit, and the girl goes forward and she smashes into the student in front of her. Maybe that's another guy. And so he moves forward and the girl moves back and he moves into this guy. And so what you see is each student, they move forward and they smash into the other person and they move back a little bit to where they were. They don't really move very far and they kind of end up where they started. So the individual people that are making up the wave, they're not traveling really, but you can actually, the rest of the students in the class over here looking at them, they can actually see the wave travel through the chain of students. And that is what we talk about when we say there's no physical transport of material. The students themselves aren't moving to, if there's a, if the wave goes all the way over here to the wall with a big long chain of students, each of these students don't go over to the wall. They stay where they are. They're not being transported. But that wave of energy, as it's pressed from one student to the next, that wave, that pulse can travel all the way to the other side. And so that's what we mean when we say there's a transmission of energy without a physical transport of material. Now, in the rest of this slide, we want to look at the sort of the parts that make up a wave. How do we characterize the structures that make up a wave? And we talk about, there's two main things that we want to talk about in this slide. Actually, I guess three. So the first one that I want to just mention is you can see this dashed line here, which represents the undisturbed state. So imagine I have a rope, and the rope is tied to the wall over here, and I've got it stretched out here. It might be stretched out along this dashed line, and no wave has started going through it. And then I might grab the other end of the rope. And shake it up and down and send a pulse, and that pulse is going to be traveling towards the wall, and we can see the wave traveling through the string, and the wave goes down and it goes up and down and so forth because the person grabbing is shaking the rope up and down and up and down. And as you see the wave travel from one end of the string to the other, you can see that there's a period at which the wave will repeat itself. And so I've got, like, for example, a maximum value here, which is called the crest of the wave, and then it goes down and it becomes negative. At the very bottom is called the trough, and you can see there's a trough here, there's a trough there, there's a trough there, there's a crest here, there's a crest here, there's a crest there. So the crest is where it's maximum, the trough is where it's minimum, and it goes from crest down to trough and then back to crest. That is a repeated motion. So you start at a crest, you end up at a crest. That repeated motion has a length called the wavelength of the wave. And so that's how long the wave has to travel before it repeats itself. That's the wavelength. Now there's another term here on this slide that we can see, the amplitude. And that's the maximum distance the wave travels relative to its undisturbed state. And I could have drawn the amplitude to the crest like here. I could also draw it to the trough. It should be the same. And that is the amplitude. It's the distance from the undisturbed state to the maximum variation. And again, we can see the direction of wave motion is showing this wave's going to the right. And so this wave is traveling like this. And so we go one wavelength, two wavelengths. The third wavelength would be off the screen over to the right somewhere. In this slide, we see another type of wave used as an example, and that's a water wave. Most people have seen water waves before. If you've ever chucked a rock into a pond or a lake, when the rock hits the surface of the water, you can see these ripples, sort of concentric circles traveling outward from where the rock hit. And these concentric circles represent the waves traveling outward. Now, what you can see, and I just want to sort of highlight one area. Right here, you can see the ripple, and if you can see, the water's kind of bunched up here, and it's bulged up, and there's kind of a peak. And then down below, the water that was here has to be kind of sucked up there to make that peak, and it leaves a valley behind. And so here is the first wave, the second wave, the third wave, and what we're seeing here is the peak. That's the maximum value. And then in the bottom of the valley here, that would be the minimum. That would be the trough. And so you can see there's the crest here, there's the trough, there's the crest, the trough, the crest, and those represent the same kind of behavior. And so you can see this sort of, in this inset little picture here, you can see the motion of the wave. And so right here is before the rock has struck. And this position 1 here would be right here. You can see this box here. So this would be position 1 right here. And position 5 would be over here on the other side and the other positions in the middle here. But let's look at position 1. So what happens is the rock hits, and then a little bit later, you get this maximum. And so there's a swell here at position 1, but that swell is traveling outward. So it's going to actually go back to the undisturbed state. And then it will go to the trough. And then this whole process will repeat as the next wave comes through. It'll go back up to the undisturbed state, and then the next wave will go through. I hope that makes sense. What you can kind of see here, imagine that you had a cork or a little buoy of some kind just floating at position 1. As the wave passes through, and again, there's going to be crest, trough, all traveling outward, that little piece of cork or whatever is just going to bob up and then bob down and then bob up and then bob down as the wave continually passes across it. There'll be crest, trough, and that cork is just going to go up and down as the wave travels through it. Note, the cork's not going to be swept over here. It's just going to go up and down as the wave passes through the water. In this next slide, we want to talk about some other properties of waves. And the two concepts that we want to cover here are what are called the period of the wave and the frequency of the wave. Now, the frequency is described here as the number of wave crests that pass a given point per second. And so imagine that you have your cork in your water here, and as the wave is traveling outward, that cork goes down and up, down and up, down and up. How many times does that cork go up and down like that every second? That would be the frequency of the wave. Now, I think there might be an easier way to understand that, because if I have, instead of thinking like the water waves, if I think of the rope that we talked about earlier that we're shaking up and down to send a wave down the rope, the frequency is how many times you shake the rope up and down. So if I grab the rope and I pull it up and then I shake it down and up, that would be one complete shake. And then down and up, that would be another complete shake. How many times per second do I shake it up and down? That's going to send pulses out like this, out down the rope. And so that is the frequency. It's the number of vibrations per second of the vibrating thing that's making the wave. But you can also think of it, again, like if I'm counting how many times a particular part of the wave goes up and down, like imagining my cork here in the water wave going, down and up, that would give you sort of the frequency of the wave. Now, the period of the wave, that's the time between the passage of successive crests. In other words, if I've got a crest passing here, the cork would be at its maximum value. How long does it take for that maximum over here to travel and get to there? So the cork's going to go down and up, and then this guy has moved over here, and the cork's all the way up again. That is the period of time that it takes for that to happen. That's called the period of the wave. And again, I think that there's another way to think of it that is kind of useful, because we already talked about how this wave is going to travel a wavelength. And by the way, I've drawn in here the typical symbol for a wavelength. That's the Greek letter lambda. Very often when you see that in physics or astronomy in some kind of an equation, lambda represents the wavelength of the wave. And so we know that the wavelength is the distance that the wave will travel to have the maximum repeat itself. Well, the period of the wave is the time it takes for the wave to travel one wavelength. So either way you prefer to think about it, either way that makes sense to you is okay with me. Now, the last thing that we want to see in this slide is this relationship here, that the period is equal to 1 over the frequency. Now remember, the period, we're saying that's the time it takes to go one wavelength. That's equal to 1 divided by the frequency of the wave. And just because of the way algebra works, we could reverse that and we could say the frequency is equal to 1 divided by the period. And so here we have a couple of different equations. Really, it's the same equation, just manipulated, but that's what relates the period of a wave to its frequency. Now, the last basic wave idea that we want to cover is the speed or the velocity of the wave. And that's basically how fast the wave is traveling. Some waves travel faster than others. And so if we think of velocity, we think of velocity as a distance divided by a time. We have a common distance and a common time that's used to characterize waves. The wavelength is how long the wave travels in one cycle of the motion. So if you're shaking it up and down, the wavelength is how far it travels in that complete cycle of the motion. and the period is how long it takes for that complete cycle of the motion to occur. And so that's the usual way that we can calculate the velocity of the wave. We divide the wavelength by the period. So we can say the velocity is equal to the wavelength lambda divided by the period, which is again usually represented by capital T. And so we can say that this is the wavelength divided by the period of the wave. And what is that? That's the velocity. And that's how you calculate the velocity of the wave. Now, there's actually a more commonly way used to calculate the velocity of the wave. So I'm going to show you one other way that we can calculate the velocity of the wave. Because we know that the period of a wave is equal to 1 over its frequency, we can take that and plug that into there. Now, you're dividing by the period, so if you divide by 1 over f, that means the frequency comes up top, and basically after you do that simple algebra, the other way to calculate the velocity of the wave is to say it's the wavelength times the frequency. And so either of these formulas can be used to calculate the velocity or the speed of a wave. In this case, it's the wavelength divided by the period, or here it's the wavelength times the frequency. Remember, frequency is equal to 1 over the period, so I could replace this with 1 over t, and that would give me just lambda over t again. But it's the same formula, just written out differently. But these are the two formulas that are very commonly used to calculate the speed or the velocity of a wave. Now, of course, when we're talking about electromagnetic radiation, as we've mentioned, it includes what we call visible light, but also the other parts of the spectrum. And so here is a figure that is showing this. And so you've got white light coming through this slit, and this slit is passing through a prism. And you guys probably all learned in grade school, if you send a beam of light through a prism, it gets split into all the colors of the rainbow. And that would be the visible part of the spectrum. We also know that beyond the violet, for example, there's ultraviolet, X-rays, and gamma rays. Beyond the red is infrared and radio. Now, one thing that's worth noting in this slide is the frequencies are increasing as you go from radio waves towards the gamma rays. And so gamma rays have the highest frequency and radio waves have the lowest frequency. You can see this little arrowhead showing which way it's getting bigger. And we see here that when you're talking about just the visible light, it's 4.3 times 10 to the 14 hertz. That's the units for frequency. That's 4.3 times 10 to the 14 vibrations per second. So that is how fast the frequency of red light would be up through violet, which is almost double that at 7.5 times 10 to the 14 hertz, or 7.5 times 10 to the 14 vibrations per second. Now, when you look at the wavelength, you can see that the wavelength is getting bigger in the opposite direction. Gamma rays have the shortest wavelength, and as you go in the opposite direction towards radio waves have the longest wavelength. So, what is an electromagnetic wave? It is a wave of coupled electric and magnetic fields that is created by vibrating or accelerating charges. Think of it like this. You learned in grade school, again, that there are two kinds of charges in the universe. There are what we call positive charges and negative charges. And you learn that like charges repel one another. So if I've got two positive charges together, there's going to be a force, an electric force between them that causes them to repel. Two negative charges, same thing. Like charges, whether two positives or two negatives, like charges repel. But what do opposite charges do? Well, you learned in grade school, you can see it up here, there's a positive and a negative. The force from them is going to attract. So like charges repel, opposite charges attract. Now, what's really important for this is just simply if you have charges, those charges are going to attract or repel one another. And so let's say that I have a positive charge over here and I shake it up and down. And there's a negative charge over here. Now, if they're just in line with one another, there's going to just simply be a force between them. But if I start vibrating this guy up and down, this charge over here is going to eventually feel a force, an electric force, tugging him up and then tugging him down, up and down. And so that is basically what the wave is. And so let's say there are some charged particles vibrating in the sun, generating electromagnetic radiation. That electromagnetic radiation travels through space, and when it gets to the electrons surrounding the atoms in your nose, it shakes them up and down. That adds energy to your nose, so that's why your nose heats up when you go out in the sun and the sun shines on your nose. So this is the basic idea of what an electromagnetic wave is. Now, it turns out that electric charges by themselves generate what are called electric fields, and moving or accelerating charges also generate what are called magnetic fields. And we'll talk about magnetism later in the semester, but just know that they're kind of like flip sides of the same coin. They're very similar to one another, and it's the two things together that make up the electromagnetic wave. Now this slide is thankfully very short. It's talking about what the speed of electromagnetic waves is. And the speed of an electromagnetic wave is given by this. C, which is usually what we use to represent the speed of light. So the C is the speed of light. Speed of light. And it's equal to 3.0 times 10 to the 5 kilometers per second. So that would be 300,000 kilometers every second. That's how fast light travels. So pretty darn fast. Now, I should be very careful because that's the speed of light in vacuum. The speed of light in vacuum is that if light enters into, say, a piece of glass, it actually slows down. And so it's only true to say that this is the speed of light in vacuum. And if light is traveling through other materials other than just moving through the vacuum of space, it can actually have a different speed. But this is the speed of light in vacuum, 3 times 10 to the 5th kilometers per second. Now, fun fact, that's actually the speed limit in our universe. Nothing in our universe that has mass or energy can move faster than that speed, which is kind of crazy when you think about it, that there's a maximum speed in our universe. It's impossible to go faster than that speed. But it's also kind of cool if you think about it too. Now this next slide, for the purposes of astronomy, may be one of the most important slides in this whole PowerPoint set. This is dealing with what we call atmospheric opacity, the opacity of the atmosphere. And so in order to understand this, we have to know what we mean by two different terms. The first word is transparent. And of course, you guys probably know that transparent means you can see through it. But another way of saying it, the reason why you can see through it is because light passes through it. So if a material is transparent, what we really mean is that light can pass through it. Now, there are other kinds of materials that light cannot pass through. We call those materials opaque. So imagine I have a door, and my door is made out of wood. Is wood transparent or is it opaque? What do you think? Well, obviously, hopefully you're all saying, well, it's opaque, because we know that a piece of wood, light can't go through a piece of wood. But if I had a window, for example, and so maybe there's a window right here, the light can pass through the window, but it can't pass through the wood of the door. So if I've got a window here, the light can go through it, but if I've got a door here, the light's going to be blocked. And so the window, we would say, is transparent, and the door, we would say, is opaque. Now, when you're talking about the electromagnetic spectrum, we know that the electromagnetic spectrum consists of a wide range of frequencies that we sort of subdivide into different regions: the radio region, the infrared region, the visible region, ultraviolet, the X-rays, and then gamma rays. And so these are the different parts of the spectrum. And here we can see this ranges in frequency from this 10 to the third hertz up to about 10 to the 23rd hertz for gamma rays. And in wavelengths, we go from very long wavelengths like 10 to the 6 over here, that'd be like 1,000,000 meters long, down to 10 to the minus 14 meters long, and even smaller than that. So the range of wavelengths of electromagnetic radiation is really huge, and the range of frequencies is similarly very huge. But let's consider frequencies. It doesn't matter which we pick. Actually, we'll pick wavelengths because there's a nice schematic underneath here. If we're looking at different size wavelengths, when you get to here, you're talking about the size of mountains. When you get to here, you're talking about skyscrapers and people and fingernails, on down to the size of atoms and even the nucleus of an atom, which is super, super tiny. That's how long the wavelength is for different things over this range. And this down here at the bottom is really the key thing. What we find, these blue regions, these are the frequencies of electromagnetic radiation that cannot pass through our air. And so wherever it's blue, those frequencies of electromagnetic radiation are blocked by the Earth's atmosphere. So if there's a star out there emitting electromagnetic radiation in this frequency, we'll never see it on the Earth because it can't pass through our air. But there are two regions where electromagnetic radiation can pass through the atmosphere, and we call these windows. And so these windows are the radio window, and so there's a wide range of radio wave frequencies that can pass through our atmosphere, and the optical window, which includes a little bit of infrared and a little bit of ultraviolet, but mostly just the visible light that can pass through. And so the optical window is the one where the optical frequencies of light, those are the ones that we can perceive, are able to pass through. If our atmosphere were made of something different, it's entirely possible that we wouldn't be able to see anything with visible light because visible light wouldn't be able to get through the atmosphere. That'd be kind of crazy, right? So it's kind of lucky that our atmosphere is made out of the stuff that it's made out of because it lets all that visible light go through. The last thing that we want to talk about is something called diffraction. Now, how do we know that light is like a wave, that light has wave-like characteristics? The answer is, well, the very first experimental evidence was that light exhibits a property called diffraction. And diffraction is something that can only happen with waves. And so if light were made strictly out of particles, you would never see diffraction. But since light is basically made out of waves, or at least one aspect of what light is made out of behaves like waves, we know that because light undergoes this process of diffraction. And so what diffraction is it's a bending of a wave around the edges of a hole or an obstacle. So I've got, again, diffraction is the bending of a wave around the edges of a hole or obstacle. And I've kind of I didn't have a lot of space on this slide to fit this all in, so I just kind of scribbled it in where I could. But here's the wacky thing. So let's say I've got a light wave coming in on a hole. Now, it doesn't work for just any hole. It has to be the right size hole. The hole has to be about the same size as the wavelength of the light that you're talking about. And for visible light, we know that the wavelength is going to be really, really small. So in order to see this effect, you need a really, really small hole. But if you are able to cut one out and you shine a light beam on it, the light bends around the hole. And so instead of just seeing a spot right here on the other side, the light gets illuminated all up and down the screen. And here's the weird thing. It doesn't just get illuminated over the whole length. There's a pattern where it's really bright in the middle, and then it gets dark. And then it's really bright again, and then it gets dark. And then it gets bright, and then dark, and then bright, and then dark. And there's like rings, these concentric rings of brightness and darkness interspaced between them. You can't get that pattern if light is just made out of particles. but you can get that pattern if light is made out of waves. And so that was the first real evidence that light is something that's made out of waves. And so that's why we've been talking about waves, because what we see coming from stars, coming from other things in the heavens, we see them from the light that they emit. We see sometimes the light that they absorb, but we're looking at light. And not just visible light, but the entire electromagnetic spectrum. And so it's important for us to understand what light is and how light behaves so that we can properly interpret those things that we see coming in from outer space. And so here in this last slide here, I've added in this definition so that maybe it's easier to see and write out that diffraction is the bending of a wave around the edges of a hole or an obstacle. And that's it for this lecture. We'll continue with Chapter 3 in the next video, which you guys can go on to now.